talk on spatial modulation. Dr. Aditya Trivedi is a professor in the ICT department of ABV, Indian Institute of Information Technology and Management, Gwalior, India. He received his bachelor degree with distinction in electronics engineering from the Jivaji University. He did his MTech in communication systems from Indian Institute of Technology, IIT Kanpur. He obtained his doctorate from IIT Roorkee in the area of wireless communication engineering. His teaching and research interests include digital communication, wireless systems, signal processing, and networking. He is a fellow of the Indian Institution of Electronics and Telecommunication Engineers, IETE, and senior member of Institution of Electrical and Electronics Engineers, IEEE, USA. He has published more than 150 papers in various prestigious international national journals and conferences. In 2007, he was given the IETE's K.S. Krishnan Memorial Award for Best System-Oriented Paper. He visited many countries for presenting his research works and has delivered many keynote talks, lectures in reputed conferences and institutes. Now I welcome Professor Aditya Trivedi, sir, to deliver his talk. Over to you, sir.
Good afternoon to organizers as well as to all the participants. So let me share the screen first. What I plan is basically simple PowerPoint presentation without involving any much mathematics, because too much mathematics in these short-term courses kill the interest actually, unless you are having full 7-8 lectures with you.
Right, sir.
So this is okay. So the title of the talk is Spatial Modulation. And if any one of you feel any doubt, any questions, then you can interrupt me any point of time as such. Okay. So these are some contents. I don't think I will be able to cover so many things. This is not possible. Just let me shift it this once again. Okay. So this actually this Zoom menu is coming over my screen. I'm just thinking how to just copy share. So this is the aspiration of a communication system designer. So basically, it's high data rate wireless communication is required with transmission rate of around 1 Gbps, because nowadays the people are trying to see the HD quality live video streaming, and also the games being played by multiple users together. With up to 4 GB, we can have this. Kind of HD quality video streaming. But if there are multiple players playing some game together, then in that case, 5G would be required, I think. So some data rate of 1 Gbps would be required in that case. And high quality of service by minimizing the probability of error. And high spectral efficiency, because as we know, the spectrum is very limited, even in UHF. And also we are now going towards the millimeter wave communication also. That is around 25 to 30 gigahertz. But this spectrum is having its own problem basically. So, but in a nutshell, we can say the spectral, we require high spectral efficiency. That means we can put as much data as possible in a given bandwidth. That is what is meant by the high spectral efficiency. And also we try to minimize the transmitted power, because the devices are handheld devices. They're having some battery, and the battery is having its own limitation. So we want to minimize the transmitted power. And also the complexity and cost of the implementation of the system should be low. Okay.
Excuse me,
this
sir.
Is another requirement. Yes, please.
Sir, are you changing the slides?
I will change now.
Okay, sir. Because we cannot able to see you are changing the slides, so that's why I just wanted to.
This has changed now. Slide has changed.
No, sir. Still in first spatial modulation.
Okay. I have changed actually. So I will stop sharing it and redo it. Okay.
Yes, sir. Yes, sir.
Now, can you see the change of the slides?
Still no, sir. We cannot able to see. Maybe you can put it in the slideshow, sir. Yeah.
I have put it in the slideshow only.
Okay.
I'm changing it continuously. Is there any change? No.
No, sir.
Still
We cannot able to see the changes. Yeah.
So should I log out and log in once again?
Sir, probably you can try you clicking the slides instead of moving the cursor.
The left
Just
side
click-
slides, sir. The left side's 1, 2, 3 slides. You can just click on the slides directly. Yeah.
Okay.
Let's just try that one. Yes, sir. Just click the
The
second
left side.
page.
Yes, sir. It's working.
Now it's working. Now it's working, sir. Yeah.
Okay, but if I put into slides show, I don't think it will be moving in that case.
So if you put in the slideshow, it should also, yeah. Can you please try this, sir?
Now, is it moving now?
No, sir. It got stuck.
Sir, actually, probably you might have sharing the particular slide. So instead, you could share the whole presentation in the Zoom.
No, I am doing that only. I will, okay. Let me
So if
try.
it is okay, you can just keep it without the full screen.
Okay, I will do this full screen for every slide. Then I will skip, then do that. Okay.
Sir, otherwise the slides are visible, sir. You
Yes,
can
sir, it's
just
visible.
maybe click the slides and then just do it, sir. No need to go for full screen also. Yeah. Yeah. Thank you, sir.
Okay. So this is the demand on the cellular mobile communication basically. So very brief history in 1 or 2 minutes time. 1G was basically the first analog system that was used in the 1970s. Then 2G came around 1990, where it became truly digital. And when we say it became truly digital, it means voice was digitized. Earlier, voice was in the analog form. But from 1990, from 2G, and the most famous example of 2G is basically your GSM system, global system for mobile communication. And still we use it, 2G system. So voice was digitized and it became truly digital system. And around after 10 years, 3G system was deployed. That is basically CDMA based, code division multiple access based kind of system was deployed in a 3G. And 4G came into existence around 2010. That basically worked with the OFDMA, orthogonal frequency division multiple access. And also this 3.5G and other things are already there. Okay. So now demand for the 5G vision. Is the slide has changed now? The slide
Yes,
has
sir.
changed? Yes, okay, good.
Yes, sir. It's changing. Yeah.
So we want this full smartphone. Tablet, PCs, and laptops are popular. We demand this real-time abilities, and also the number of connected devices are increasing because also the data rate is increasing as well as the number of devices are also increasing. Nowadays, if normally a person is keeping 2-3 mobiles with it, together with the other devices like laptop and other things, all are basically generating the wireless traffic basically. So in the 5G system, which is expected to exceed the 4G capability in different ways, like a 1000 times increase in the capacity. That means suppose that one particular 4G cell is using say 1000, but the 5G in the same cell would be using 1000 into 1000 number of devices per cell. That is 1000 increase in the number of devices, 10 time increase in the data rate around 10 Gbps, 10 times spectral efficiency, and as well as 25 times cell throughput. And also the access time is going to be less than around 1 millisecond. So these were basically the 5G vision actually. And now the 5G in India is being rolled out in 1 or 2 parts. It is being launched in some part of the country. But I think the full-fledged deployment of 5G will take another 2 to 3 years time basically. Okay. So how 5G can increase all these capacities, data rate, number of connected devices, so many things. So basically there are various technologies available. And still please remember, some of the technologies which are being proposed for the 5G, they are also being modified, they are also being researched, and they might be used if not in the 5G, then they might be used in the 6G also. So there's basically some 5G area and 6G areas being overlapped, actually, you can say like that. So basically we are having this dense microcells, massive number of antennas per base station and devices, beam forming antenna patterns. So there are various technologies which can achieve this task. So dense microcell, we are splitting the cells again and again, and we know that if we reuse the same frequency again and again, in that case, we can increase the capacity. Number of antennas can be increased. So massive MIMO kind of thing would be there. Beam forming antenna patterns would be there. So that basically we get the radiation from the mobile, which we want to receive the signal from where we want to receive the signal. And we can avoid the interference from the other mobile devices. And we can use millimeter waves. Cognitive radio is already known to most of you. Relay station, we want to increase the capacity or the coverage by using the relay station, because if you are not able to, base station is not able to communicate to a far-flung area, then any device or any other equipment can be used as a relay station. Through that, we can connect it to some other device. This is a relay station. Then NOMA, I think some of you might be aware of that. NOMA, non-orthogonal multiple axis. And up to 4G system, we were using orthogonal multiple axis. Orthogonal multiple axis means basically the frequencies were basically to each other. But in the case of NOMA, the frequencies are not kept to be orthogonal. In fact, they are basically allowed to overlap with each other. So then what is the point of going for overlapping of the frequencies? Basically, it will increase the number of number of devices. It can increase the number of devices, and this interference, because of this non-orthogonal multiple axis, is kept deliberately there small, and this is basically eliminated using SIC and other methods, successive interference cancellation and other method. But today's talk is basically focused on the spatial modulation. So what is spatial modulation and how it can increase the data rate and other things that we will see now. So this is basically, this picture shows the single input, single output conventional radio system. So here we can see this user data stream is there on this side, and I'm just putting my this mouse over here, and this is the output side, and in between is the channel basically. So the single input, single output is having only one single antenna at both transmitter and the receiver. So we can still go to 1 Gbps barrier using this particular configuration. Only thing you are required to pump more power at the transmitter side, and you require large bandwidth. But we know that in the wireless network or in the wireless system that we are having constraint on both. We are having constraint on power as well as on the bandwidth. So it's very difficult to achieve 1 Gbps barrier in that case. So, but a combination of a smart modulation, coding, and multiplexing technique can still can yield good results, but is still far from the 1 Gbps. So that's why we are switching from CISO to MIMO system. In the MIMO system, we are having multiple antennas at both the sides, at the transmitter side as well as the receiver side. So this is the picture where we can see on the left-hand side is the transmitter and transmitting antennas, and the right-hand side is we are having receiving antennas, and in between there is a channel like that. So we can use multiple antennas at both transmitter and the receiver. This system is excellent in terms of capacity and quality, because it is basically creating multiple beams, multiple streams rather, multiple data streams. And these streams are being received at the receiver side antennas. So MIMO system basically increase the spectral efficiency. So we can transmit the data rate at a pretty fast rate, because we can use serial to parallel converter at the transmitter side, and we can transmit the data from the multiple antennas in parallel. Basically, it creates a parallel kind of channel. Another thing which I would like to mention is that MIMO can be used, this MIMO configuration can be used in a number of ways. For example, this can be used for your diversity advantage. Diversity advantage basically means if you are sending the same information through parallel streams through multiple antennas, then at the receiver side, you are receiving the same information at the multiple receiver antennas. In this case, basically, you are creating transmit diversity as well as receiver diversity. And the diversity basically means sending the same information through parallel path, only thing that you are required to remember is that the parallel path should be independent. Because if there is some problem with the one path, it should not go to the second path. They should be independent. For example, if one path goes into the deep fade, not all the path should go probabilistically in the deep fade at the same time. Otherwise, this diversity advantage would be lost, and there is going to be no reliability in the system in that case. So what happens is that you create a number of parallel paths by putting antennas just few centimeters apart. For example, now suppose that you are operating at 5 gigahertz. So 5 gigahertz, we can understand that what is the wavelength. And then if you keep, it is only few centimeters only. If you keep antennas few wavelength or few centimeters apart, then it will create parallel path, and they are going to be independent of each other. So that is one advantage of doing using MIMO system. Another is you can use it for the spatial multiplexing. Spatial multiplexing means basically you can use serial to parallel converter, and you can enhance the data rate. You can enhance the data rate. So this is known as the spatial multiplexing. Another way you can use a MIMO system is SDMA, spatial division multiplexes. There one particular transmitting antenna is transmitting to one particular mobile. Second transmitting antenna is transmitting to second other device, like that. So this is known as spatial division multiple access, SDMA system. So there are a number of ways we can use the MIMO system, and also we can use the MIMO system in more than one mode. For example, we can achieve diversity as well as spatial multiplexing together, like that. So there are various ways to do that. So MIMO is having so many advantages basically, but there are also some challenging issues with the MIMO, because it is easier said than done, because there are some problems with the MIMO system. For example, the MIMO system is significantly affected by the spatial layout of the transmitting antennas and receiving antennas, and also synchronization is required among the transmitting antennas. Otherwise, what happens is that inter-channel interference will arise at the receiver side. Inter-channel interference will be there in case there is no synchronization at the transmitting antenna side. So basically, for the MIMO system, one very famous algorithm is used, that is basically known as V-blast system. This is your Bell Labs layered, vertical layered space-time architectures was basically used to counteract the inter-channel interference. So what happens in the case of V-blast? It basically separates the multiple transmission and data stream and detect them successively by an array processing and interference cancellation kind of technique. So this technique is also very complex actually, and a lot of computational complexities involved in that. Okay. So this is OFDM, I am skipping that. So why we are going for a spatial modulation in 5G or 6G basically? So the main drawback of any MIMO system is an increase in the complexity and the cost. Now basically there are three reasons why this complexity is increased in the MIMO system. One is the inter-channel interference, which I just mentioned, because there are multiple symbols are there in the time and space. They are coupled in time and space. For example, if I am transmitting from one antenna, due to the wireless channel's broadcast nature, the same information would be received by all the receiving antennas. But here in the MIMO system, I am transmitting in parallel from multiple transmitting antennas, and all these information is going to be coupled to the receiving multiple receiving antenna. So that's why there is an inter-channel interference would be there. Another thing is that the detection algorithm at the receiver side assumes that all the symbols are transmitted at the same time. That means there is some internal synchronization is there. If it is not there, the problem becomes more complex at the receiver side to detect it. And also, suppose that you are using 4 cross 4 MIMO system, that is 4 transmitting antennas, 4 receiving antennas, and the 4 transmitting antennas, you are required to use 4 radio frequency chains basically. And all these chains are basically transmitting in parallel. So, and we know that basically radio frequency chain consists of number of LPS, LNN, low noise amplifier, and other things, filters and other things. And every radio frequency chain is having its own cost basically. So that's why this MIMO system is having many problems also. So how to overcome these problems basically? So spatial modulation is the technique basically where we can get rid of these problems. So what is spatial modulation? So spatial modulation is basically defined as a hybrid modulation of conventional QAM kind of system, conventional QAM amplitude and phase modulation. And also together with QAM, we are also introducing another dimension that is known as the antenna indices. So spatial modulation is a combination of QAM plus antenna indices, index you can say. So it is having three-dimensional constellation. Two-dimensional constellation is reserved for this QAM, where we denote the amplitude and the phase. And the third dimension is basically for the antenna index, basically. So we also encode the source information into the antenna index. We are encoding the information in the QAM symbol as well as in the antenna index. So antenna index is also basically carrying the information along with the standard QAM symbol. So that is why spatial modulation is different from the other MIMO technique. So now, basically, since the antenna index plays an important role because antenna index also carries the information. I will explain it by giving some examples also later on. Don't worry about that. So suppose that there are 4 antennas. So we can put 2 bits per antenna. For example, 0, 0 denotes the first antenna, 0, 1 denotes the second antenna, 1, 0 denotes the third antenna, and 1, 1 denotes the fourth antenna. Now the question is that, suppose that you are transmitting from one antenna, then what is the actual physical location of the antenna is very important because the receiver should know that the signal is coming from which particular antenna. Then only it can decode 2 bits of additional information, which is being sent by the antenna index. So that is how we are doing the things in the spatial modulation that we are going to see now. Okay. So another thing is that at the receiver side, basically, we are using iterative maximum ratio combining IMRC algorithm at the receiver side. So this is a tridimensional constellation diagram. We can see here. Basically, you can see these blue dots. So I'm putting my mouse over here. This blue dots, 1, 2, 3, 4, they basically denote the antenna. They denote the antenna. And each antenna, now we are having a constellation like this. Suppose that this is your real axis. This is vertical is your imaginary axis. So now there are 4 dots, red dots. They basically represent the 4 symbols. And also the red dots, we are having 0, 0, 0, 1, 1, 0, and 1, 1. So this is your standard QPSK kind of symbol. Or in general, you can say basically it's a QAM, quadrature amplitude modulation. Same symbol is also in the red in the 4th antenna, we can see dots and 1, 1. So here we can see this X, Y, Z is there. The axes are there. X, Y is basically used to denote the phase and amplitude information, which is used in the QPSK or QM is a standard modulation technique that we know. And the Z-axis basically represent the antenna index. That is where we are going to stuff additional information. For example, now we are having 4 transmitting antennas. So antenna number 0 is corresponding to 0, 0. Antenna number 1 is corresponding to 0, 1. Antenna number 2 is corresponding to 1, 0. And antenna number 3 is corresponding to 1, 1. I'm numbering the antennas from 0 to 3. You can number it from 1 to 4. So overall, there are 4 antennas. So basically, the antenna index carries 2 bits of additional information, 0, 0, 0, 1, 1, 0, and 1, 1. For example, now if you concentrate here in the first, okay, go to the first constellation diagram. Here in the black, I can write 0, 0, 0, 0, 0, 0, 0, 0. Basically, this 2 additional bit information is being sent because of the antenna index 0. And if you concentrate on the last constellation diagram, which is in the frontmost, you can say, we are having 2 black bits 1, 1, 1, 1, 1, 1. These 2 1, 1s are basically coming from antenna index 3. So right from 0, 0 to 1, 1. Suppose that in the antenna number 1, same red dots would be there, but the antenna index would be now going to be 0, 1. From the antenna number 2, it is going to be 10 black, like that. Because the bits from the information source can come in any sequence, So we are considering all the 16 possible combinations consisting of 4 bits, right from 00, 00 to 11, 11. Because if you could see here, this is your 00, 00, and here it is 11, 11. All possible combinations would be covered. But please remember, we are sending only 2 bits of information through your standard QAM signals or QPSK signal, and additional 2 bits of information is being sent only through one of the antenna. So here antenna index is also sending the information. Okay. So this is what I just explained to you. XYZ space represents spatial constellation. XY plane represents signal constellation, which I told you whether it is the QAM or QPSK. Z-axis represents the antenna indices. Signal constellation is defined for every antenna index on Z-axis as shown in figure 2. Okay, so here this is little, I'm trying to put it the slideshow so that we can see it little more clearly. After that, I'm going to change. If the slide does not change, I will revert to original this minimize mode. Okay, so here we can see this is your transmitter site. 4 antennas are mentioned over here right now, but in general, it could be antennas could be there. Similarly, at the receiver side, we are having NR number of antennas. Receiving antenna 1 to NR is there. Now, this is the input side to the transmitter, where we are having N bits which are being sent to the spatial modulator. This spatial modulator is now expanded in the below diagram. You can see. So this QK stream is coming, which is having a separator because it separates the stream into 2 parts. For example, if you consider the previous example, the 2 bits are reserved for the QPSK and the next 2 bits are reserved for the antenna index. So similarly, the separator does the same thing. It reserves first 1 or 2 bits for the antenna index encoder and remaining bits for the signal modulation encoder as per the standard your QAM or QPSK protocol. So what happens is that the QAM is there, QK is there, it's separated, then it basically generate XK symbol. Okay. Now the idea is that very simple. Idea is very simple. If you just concentrate, the first 2 bits separator antenna index encoder will choose from which antenna you are required to transmit. In the previous case, we were having 4 transmitting antennas. So 2 bits would choose, first 2 bits will choose which antenna is to be chosen for transmission. First 2 bits could have only 4 combinations 00, 01, 10, 11. So basically, what are the values of the first 2 bits? Based on that, you can choose the antenna index. From the remaining antenna, you are transmitting null. You are not transmitting anything. So that's why in the XK, you can see, although we are having anti symbols, but except one symbol, all are nulls, all are zeros, basically. You can see, concentrate here, like that. This is the thing, you can concentrate over here. And I'm putting my mouse over here. Only one antenna would be activated. Only one antenna would be involved for transmission. And what is to be transmitted from that active antenna? That is being given by the standard QAM or QPSK symbol, like that. So next 2 bits in the, for example, whether it's 0001, 1011, that would decide what is to be transmitted from that symbol or from that particular antenna. But only one antenna would be activated. Now, how these things are going to help us, that we will see just now. Okay. After this, there is a channel between the transmitter and the receiving antennas. So this channel is basically given by the channel matrix. So we can say this is the channel matrix. Okay. And we can see basically this is your NR cross NT. NR rows are there and NT columns are there. NT columns are there. So it is row wise, it is NR, and column wise, it is NT. NR cross NT channel matrix would be there because if you are even if you are transmitting from one antenna, this is going to be received by all the receiving antenna. Also from the second antenna, you are transmitting any signal, this is going to be received by all the receiving antenna. So basically, this channel, wireless channel, is to be characterized by this and NR cross NT matrix. At the receiver side, YK is the received symbol, YK is the received symbol, and this passes through the detector IMRC, and basically it detects the antenna index, and also using this spatial demodulator, it also detects the what was actually transmitted, and hopefully you will recover your information back. Is the slide has changed or not? Yeah.
It's changing, sir. So now you are in this block diagram of spatial modulation, right? Yeah.
Block diagram. After that, I have changed the slide. It's not changing now. Don't worry.
No, sir. Still
No,
in block
okay,
diagram.
don't worry. If there is something important, then I will use.
Yes. Now it's changing, sir. Yeah.
Okay. Transmitter. So transmitter includes spatial modulator and number of transmitting antenna. And this thing I just explained to you, so there is no need to. So the separator separate information bits into two blocks: antenna bit block and signal modulation bit block. Same thing. Receiver also I just mentioned to you. How it works basically. Spatial modulation is used to map a block of information signal into two information carrying unit. One symbol that is chosen from a constellation diagram, and a unique transmitting antenna number that is chosen from a set of transmitting antenna. I will give examples of that also, so that the picture would be very clear to you. Constellation diagram depend on the number of bit transfer. Okay. So an input signal QK includes n bits. For example, the QK could be 4 bits. So the spatial modulator is, modulates QK to XK. So basically what happens is that the 4 bits, I'm taking example of 4 bits, so because I have previously taken 4 bit, so that we can understand the things quite clearly. Otherwise, this could be extended to any number of bits. So basically, two blocks are like this: log to NT and log to M. NT is the number of transmitting antenna. For example, I am using 4 antenna, so log to NT equals to 2 bits. And if I am using 4 size constellation diagram, that is QPSK or QM, 4QM or 4QPSK, you can say, then we are having log to 4, that is 2 bits. So 2 plus 2, n bits, that is 4 bits could be transmitted per symbol from per antenna. Because the antenna index is also being transmitted at the same time. So log to NT is the number of bits that is transmitted as per the antenna index. And log to M is actually using this QM we are able to transmit. So total n number of bits could be transmitted like that. Is that clear? Any questions over here, please? Any question? Any doubt?
No. I have. So one question.
Sir, yes, sir. I thought to ask in the last, but since you have asked, as of now, I'm clearly following your whatever explaining. But I have a curiosity that, sir, in this approach, we are already deciding based on the antenna number that which symbol is going to be transmitted by which antenna.
Mm-hmm.
But can we incorporate, sir, some technique like based on some matrices like SNR between two antenna pairs, which antenna pairs having the say high SNR will stream a particular symbol to that antenna pairs. Can we go for this approach? Because we are not looking for this SNR between two antenna pairs. We are just pre-deciding the symbols which is to be decided by which is to be transmitted by which antenna.
So what you are basically saying is a kind of you can as a selection diversity or some kind of thing. Basically, there you are
Yes.
you are using the strongest path. There the idea is different. There in your question basically you are basically after the reliability. You want to increase the reliability. Here the problem is different. Here I am trying to increase the data rate.
Okay.
That is the difference actually. Here
Yes, sir. So can we, sir, can we integrate these two things? Is this idea, sir, good or, sir? I mean, it has some limitation.
Yes, definitely. Yes, actually in spatial modulation, there are many variations are there. So this idea could be used also. In fact, although I will not be able to cover it, but the thing that you are just mentioning is already being done actually. Okay.
Okay.
But first, I am trying to emphasize the basic concept of that. After that, there are a lot of variations are already there in the spatial modulation. This is also being combined with the telescope modulation. This is also being combined with the space-time block codes like that.
Okay. Thank you, sir.
All these things that you are asking is already taken care of. Most of the things. Okay. But
Okay,
if you are asking about the plane spatial modulation and the technique that you are asking, basically in that your case, it is the reliability which is more important. Right now here sending increasing data rate is more important, together with additional advantage which I will just mention to you.
okay, sir.
Okay, I think this we have already seen it. Okay, so there is no point in. Okay, so how it is to be done at the receiver side? So that I think I will explain later on when we discuss the. Let's see the example first, because this will make the things quite clear. So we are having this 4 antennas are there, and we are going for 3-bit BPSK, and we know that in the binary phase shift keying we can transmit only 1 bit per symbol. But here we are able to transmit 3 bit per symbol because we are using 4 antenna spatial modulation technique. So what happens is that here antenna number 1, 2, 3, 4 are there, and they are being given as 0, 0, 0, 1, 1, 0, and 1, 1, for example, like that. So as we know that the bits can come in any combination. They can come in any combination. For example, if we are getting 0, 0, 0, then the first 2 bits will look for the antenna index. In this example, the separator would separate the first 2 bits and it will go to the antenna index. That means now the followed bit is to be, or the followed symbol is to be transmitted from that antenna. So 0, 0 will basically point towards the antenna number 1, and 0 is to be transmitted from the antenna number 1. If we are on the other end, we are getting 0, 0, 1. Again, the first 2 bits will suggest that we have to transmit it from the antenna number 1. But what is to be transmitted is bit 1 now, not 0. Similarly, if the bits are coming in the combination, for example, 1, 0, 0, like this 1, 0, 0. So 1, 0, 0 will basically tell you the first 2 bits 1, 0. That means you are required to use third antenna. And the third bit is 0. That means you are required to transmit single 0 bit from the third antenna. But at the receiver side, if we come to know that this 0 bit is coming from the third antenna, then in fact we are able to decode 3 bit of information 1, 0, 0, not a single bit of information. We are increasing the data rate without any additional cost actually. But please remember, we are transmitting only one antenna at one point of time. Only one antenna is being used. And suppose that in the last you are having 1, 1, 1. So first 2 bits would be reserved for picking that antenna index, which is antenna number 4 in this example. And the last bit 1 is to be transmitted from the antenna number 4. Again, at the receiver side, if we find out that this transmission is coming from antenna number 4, then we can decode the bits as 1, 1, 1 like that. Okay. Similarly, another example is there. Here we are using only 2 antennas. 3-bit 4QM. I am taking simple examples. We can increase the number of bits and the QM size also and number of antennas also. So here in the 3-bit 4QM example, this time we are having since 2 antennas. So only the first bit would be used to denote the antenna index. Remaining 2 bits would be used to denote the in fact pick the particular symbol from the QM or QPSK constellation, PSK constellation. In general, basically it is a QM constellation. So first, for example, if we are having 0, 0, 0, the first bit would be used to pick the antenna number 1. Remaining 2 bits 0, 0 would be used to choose the constellation symbol from the QM, which is going to be, say, for example, -1 or +1 + j, for example. 0, 0 is corresponding to +1 + j. You can choose any style. You can choose any particular configuration, any particular protocol you can use. But this should be known to the receiver also at the same time. Okay, that means 1 + j stand for 0, 0, or 1 + j stand for 1, 1, whatever it is. But should be known to the receiver beforehand. What the receiver doesn't know is that which particular bit is coming to it. Okay, but once it identifies that this particular bit is coming to me, then it can always decode it as per the standard decoding rules at the receiver side. Okay, so this is another example where we are using 3-bit and 4QM, 2 antenna spatial modulation kind of system. Okay. Okay. So what is important here is that now the important thing I'm going to focus is how to decode the information at the receiver side. So the received vector yk is iteratively multiplied by the channel path gains. So for example, here, if I go back to that figure once again, okay. Yk is basically the received vector, which we can see. This is HF is the basically the gain of the channel. XF is the symbol which is transmitted from F antenna. Okay. And WK is basically the additive white Gaussian noise factor. Okay. So YK is the received, which consists of transmitted signal multiplied by the corresponding channel gain, corrupted by the white Gaussian noise, like that. So now come back here over. So this is how we are going to decode the information at the receiver side using iterative MRC receiver, maximum ratio combiner receiver. So YK is received, and this is being iteratively multiplied by the channel path gains. I will give example also how to do that, which are assumed to be known at the receiver. Although one requirement is that it is assumed that the channel estimation is being done beforehand. If the channel is changing, again, you are required to go for the channel estimation. So I'm not focusing on the channel estimation part. It is assumed that the channel is estimated at the receiver side beforehand. Is iteratively multiplied by the channel path gain, which are assumed to be known at the receiver in order to estimate both. So what you are required to estimate at the receiver side, you are required to estimate both the transmitted symbol as well as the transmitting antenna number or transmitting antenna index. So what this Y is known to you, Y vector is known to you. This is being multiplied by the channel gain matrix. I will give example, don't worry about that. And this is to be done iteratively. You pick any of the column, multiply by Y. And here H stands for the Hermitian transpose, basically. Hermitian transpose. So you can calculate Gj, where J is going from 1 to NT. And we know that in the H matrix, H channel gain matrix, there are NR rows, NT columns were there. So you pick one column from the channel gain matrix because you do not know that the transmission is coming from which particular antenna index. So that's why you have to deal with the complete NR cross NT matrix. Pick one column, multiply by Y, take the Hermitian transpose, multiply by Y, you will get G1 for the first column. For the second column, you will get G2. Up to you will get GNT. So this G vector is basically consisting of G1 to GNT. These are all basically entries in this G vector. So after this, you are required to calculate which of this G1 to GNT is having the maximum magnitude. So you have to go for the maximum maximum magnitude of G. For example, the second is having the maximum magnitude. That means that particular symbol is coming from the second antenna index. So F basically denotes, F dash denotes the estimation of the channel, estimation of the antenna index number, which is nothing but the maximum of the magnitude of the G vector entry. I will give example and then we will see this better. Once you know, find out, okay, G2 means that is the symbol is coming from second transmitting antenna. Already number of bits would be decoded based on log 2 NT. These bits would be decoded. Moreover, what is inside the G2 that you can decode as per the standard quantization function. It's like you do it for the QAM signaling. So now we can see method of detecting of transmitting 3-bit signal by MRC in the case of 2x4 antennas and 4 QM modulation is described. So what is being followed? We are transmitting from 2 antenna, 2x4. We are receiving signals from the 4 antennas. So 2 transmit, 4 receiving antennas are there. Okay. So basically NR cross 4 cross 2 channel matrix would be there. And we are using 3-bit spatial modulation. 2 bits as per the standard 4QM modulation would be used, and 1 bit as per the antenna index, because we are using 2 transmitting antenna. So 1 bit would be decoded by the antenna index. So this is the problem. Okay. So now the following sequence of the bits to be transmitted: QK011. For example, the information source being gave me 011 bits. Now I want to transmit 011. So what we do basically, the spatial modulator maps an input signal 011 to 4 QM symbol and 2 antennas. Okay. The first bit would be used to highlight the antenna index, and the remaining 2 bits would be used to pick a constellation from the QM symbols. So the resulting vector xk would be 0. That means we have to transmit from the antenna number 0. And what you are required to transmit in place of 11 is basically encoded as -1 minus j, minus I, -1 minus I. 11 I am encoding as -1 minus I. So -1 minus I is to be sent. And you might be knowing how we are doing it using this real axis and imaginary phase. We can pick a point corresponding to that we sine cos function. We send one particular waveform. As such, it is we are not sending any -1 or minus j, but numerically we can establish and we can show that it is -1 minus I is being sent. Basically, we are picking one sinusoidal wave corresponding to that, and we are sending it. Okay. So -1 minus I is to be sent from the antenna index 0. Okay. So first antenna send -1 minus I, and the second antenna send 0. That is, sends null. There is no signal energy would be required. Nothing is to be transmitted from antenna number 2. Now this is your channel gain matrix, which already calculated. Right now we are not considering the noise effect, so we are going to get the perfect answer. But even if you consider the noise effect and noise is not very, very strong, in that case, you will, using this quantization, you will get the correct result. But right now we are not considering as such any noise effect. So we get the perfect result for better understanding. So now we know that the size of the antenna, size of the channel gain matrix is 4 cross 2. 4 receiving antenna, 2 transmitting antenna. So we are having 4 rows and 2 columns, we can see. And the channel gains are complex in nature, so it's having a real part as well as the imaginary part also. Okay. And please remember, we are sending the information from the first antenna. Second antenna is sending null, nothing. So once you, the receiver receives the vector expressed as, we are not considering the noise over here. So since the same signal which is being transmitted from the first transmitting antenna would be received by the 4 receiving antenna, because the when the wireless channel is broadcast in nature, so whatever is being transmitted would be received by all the receiving antennas. So we are having since 4 receiving antenna, so all the 4 receiving antenna would receive the signals like, first example, we are having 4 entries here, 1, 2, this is 3rd, and this is 4th. Okay. So we are having 4 receiving antenna receiving the signals. Now, after this, we apply the IMRC detection algorithm. That means this YK is to be multiplied by sorry, let me finish. Okay. By one of the column of the H matrix. We pick first column, multiply, and the multiplication you have to make sure that becomes 1 cross 4 into 4 cross 1. So result is 1 cross 1. One scalar quantity would be there. Second time you pick second column. Second time you pick the second column and multiply again. So you will get 2 entries in the G matrix, G vector. So the entries would be like this: -1 minus I, minus 0.3271 minus 0.2978 I. If you multiply, you will get only this result. You will get, we have done this calculation, so you will get only this result. So now now this GK vector is having 2 elements, -1 minus I and minus 0.3271 minus 0.2978 I, which is having the maximum magnitude that we can find out very quickly. by taking the real part square plus imaginary part square, taking the square root of it. Then, of course, the first one is having more magnitude as compared to the second element of that. So what we know that now, that immediately we will come to that conclusion that this being transmission was done from the first antenna. So immediately the first bit is going to be decoded. And -1 minus I is corresponding to 1, 1. That is as per the standard decoding procedure. Because we have used the same encoding procedure at the transmitter side. 1, 1 was encoded as -1 minus I. At the receiver side, we just do the reverse operation, decode it. So what happens is that we recover our complete information 0, 1, 1, which was actually transmitted. So in fact, we have sent only 2 bits, but we have received 3 bits of information. This is the advantage of spatial modulation. I used a very simple example so that we can follow the things in a better way. Now, this is some complexity calculations are there. I'm going to skip it. So the idea is that if you compare the spatial modulation with the V-blast system, the complexity offered by spatial modulation is many, many times lower compared to V-blast system. So that means complexity wise, it does a lot of reduction in the complexity spatial modulation. Now, what is the advantage of working with the spatial modulation? So advantages are many actually. So your spatial modulation entirely avoids this inter-channel interference and inter-antenna synchronization. Why? Because the reason is that we are transmitting only from the single antenna. We are not transmitting from all the antennas. We are using only single transmit antenna. So inter-channel interference is reduced. It's basically avoided actually, totally avoided. Because inter-channel interference happens when one receiving antenna receives information from multiple transmitting antenna. Then only your inter-channel interference takes place. On the other hand, you are having this inter-antenna synchronization. Inter-antenna synchronization means the reduction algorithm at the receiver side in the MIMO system assumes that all the symbols are transmitted from all the transmitting antennas at the same time. But as such, there is no problem of inter-antenna synchronization. The reason is that because we are transmitting only from a single antenna. So there is no question of inter-antenna synchronization. So we are avoiding 2 main problems of MIMO system. One is ICI, inter-channel interference. Second one is your inter-antenna synchronization. And also the third problem is that it requires a single RF chain at the transmitter. In the standard MIMO system, suppose that you are using 4 transmitting antennas. So you require 4 radio frequency chains basically. All are costly. Here you are using only single radio frequency chain. Only thing you are required to switch it to which particular transmitting antenna you are using. So you are required to switch this RF chain, that's all. So you require only single radio frequency chain at the transmitter side. That reduces the cost also. Also, the spatial modulation basically increase the spectral efficiency because now you are able to transmit more number of bits as compared to your traditional QM system. So SM can efficiently work even if the number of receiving antenna is less than the number of transmitting antenna. Okay. So another thing is that the design is very simple. Complexity is very less. It avoids ICI, IAS. Requires only 1 radio frequency chain. As such, there is no constraint that NR should be greater than NT, which is there in some of the algorithms. As such, this constraint is also not there. So this is the advantage. But there are some disadvantages also because there is nothing free in the world. So every scheme is having its own advantage and disadvantage. So you require at least 2 transmitting antenna to exploit the SM concept. But so is the case with the MIMO system also. You require at least 2 transmitting antenna. Otherwise, you are not going to get any gain out of it. Second is if the transmitter to receive wireless links are not sufficiently different. If they are not sufficiently different, SM paradigm may not be used or might not yield adequate performance. That means the idea is the same as the MIMO, like that. The 2 transmitting antenna, they should be sufficiently apart. They should be sufficiently different. Because if the channel gain is same, coming from both the antennas are same, in that case, the receiver algorithm would have a difficulty that from which particular transmitting antenna the symbol has come. That means two transmitting antennas should have a sufficiently apart. But nowadays, we are going to higher and higher frequencies, gigahertz. So two transmitting antennas could, even if you put only few 10 centimeters apart, that would be enough. That will create independent path, and that will create separate channel gains for that path. So we can easily identify which antenna index the particular symbol is being transmitted. Another thing, the receiver requires perfect channel knowledge. So is the case in most of the other algorithm also. But the real drawback is the last one actually. The spatial modulation can offer only logarithmic increase of the data rate with the number of transmitting antenna in place of linear. For example, if I am using 16 transmitting antenna, so I can send 4 bit of information, additional information, not 16 times more data rate, as is the case of some spatial multiplexing MIMO system. But the MIMO system is having its own disadvantages, which we have already discussed earlier. So the limitation of the spatial modulation basically comes from the capacities increased logarithmically, not linearly. So at very high data rate, very high data rate, either you require large number of antennas or the scheme will have its own limitation for that. Now, as some of you might ask the question, although it's not time to go into the details of each of the spatial modulation, but there are different kind of spatial modulation system exist. One is adaptive spatial modulation. Basically depends on the channel condition. So channel conditions. So based on that, it can go to the lower modulation technique. For example, we know that BPSK is the best modulation scheme because it requires minimum SNR to achieve a given probability of error performance. So if the channel conditions are very poor, then we can switch to the BPSK. If the channel conditions are good, then we can switch to the higher modulation scheme like 16 QAM or something like that. The adaptive spatial modulation can be coupled. Spatial modulation can be coupled with the adaptive things basically. So there is going to be some feedback link also. So the feedback link is basically linked to give the channel information. If the channel is good, accordingly we can change it. Things like that. Also, this is some performance. Telescope. Telescope can also be used in conjunction with your spatial modulation. So that will also give you tremendous advantage. Tremendous coding end would be offered. So these things are already there. So basically some traditional communication theories also being coupled with the spatial modulation, and overall we get the advantage of that. Similarly, we can have this, another thing is just, we can use it for this with the block code also. Space-time block code can also be used with the spatial modulation. So this, and there are a number of different variations of spatial modulation is there basically. So all these could be used, and this is also an active area of research also. We can also continue to research other kind of spatial modulation basically would be your fractional bit encoded spatial modulation, bit interleaved coded modulations like that. So now if you're having any questions, I welcome the questions.
Thank you very much, sir. Thank you very much for the insightful talk. Sir, I have a couple of questions.
Yes, sir, please.
Sir, is there any difference between this index modulation and spatial modulation, or is it the same? Index modulation and spatial modulation.
Actually, I'm not very much aware of the difference as such, but I know about the spatial modulation where index is carrying the information.
Yes, sir. So that is why I asked this question, because it's about the numbers, right? Antenna index numbers. So that is what it is carrying.
Basically, this spatial modulation is also known by some other names.
Okay.
Maybe this could be the same thing. Yes.
One more question. So how you are going to decide this active antenna and inactive antenna? Like what makes that?
Actually, I told you that there is a separator which separate the block of bits into two parts. One, for example, if I am using 4 antenna, transmitting antenna, then the first 2 bits would be reserved whatever may be the value of the first two bits, because the bit pattern we cannot control, it is coming from the information source. So either it's a 0001, 1011, whatever it is. So suppose that you are having first two bits as 10, that means you are transmitting from the second antenna. And what is to be transmitted depends on the next two bits. If we are using 4QM, 4 transmitting antenna kind of system. So the first two bits in the separator will decide. If you are using 8 transmitting antenna, in that case, the first 3 bits will decide which antenna is to be activated.
Right. Okay, sir. Yeah. Sir, and you mentioned that the channel state information is, they're considering it as a known case, right? So what about like if the channel state information is unknown?
If you do not know the channel state information, then this MRC algorithm will not work. But this channel state information is usually available at the receiver side, because although I did not discuss it, but there are some standard channel estimation algorithms like MMSC and other algorithms are there, which estimate the channel, I think, quite comfortably and also quite accurately also. So this part I did not focus on that, but it is assumed that this information is available.
It's known. Okay.
Otherwise,
Thank you very
this IMRC will not work.
Right, sir. Thank you, sir.
Because you have to multiply this column of the H matrix with the receipt vector. Then only you can get the G vector. And from the G vector, which element is having the highest magnitude, that will be your basically antenna index.
Okay, sir. There are some questions from the participants, so I'll just read out those questions. Yeah.
Yes, please.
All modulation techniques, will it be suitable for the intelligent? This is not suitable for this topic, sir, but they're asking about intelligent reflecting surfaces. So all modulation techniques, is it suitable for IRS?
Maybe he's asking this spatial modulation is
IRS,
for that.
intelligent reflecting surfaces, where basically you change this phase information and other things. So you can increase the capacity of the wireless system by transmitting over some passive surface, which reflect the beam in some direction based on some phase and amplitude, isn't it? This is the same IRS now you are talking?
Yes, that's right, sir. Yes, sir. Yeah.
Okay. So I think UPSK and BPSK are being used right now, it seems, because one of my students is also working in this IRS.
Oh, okay, sir.
Basically, how much? Basically, what you are doing in the IRS, you are intelligently reflecting it. So you can increase the coverage of the, for example, your coverage of the wireless system. For example, there are two kind of users are there. One is LOS, another is NLOS. LOS means line of sight, another is NLOS. LOS direct path is available, so I think the signal is quite strong. So you don't use it. LOS, you are not using anything. But when NLOS, the customer is very far off from the base station, then probably you are going to use IRS so that it can increase the coverage region of that. Yes. So, but I think number of phases should also be controlled. It should not be like 128 or 350 or 256 QM, because this may be some problem at the IRS surface, how beautifully you can control the phase. So there is going to be some kind of limitation, but I think in general.
Yes, sir. So I think there is one more question from Dr. Satish.
No, I already asked sir when he has asked in the between. Sir, there is one more question, but it seems like that you have already answered. It's regarding IRS only, so we'll not take that. Okay. So, sir, for me, it was really interesting talk, because I heard this term spatial modulation, but never got time to go through that. So it was nice for me. I came across this new topic, spatial modulation. It's really interesting, and I hope it's also interesting for all the participants. So thank you, sir.
Thank you, audience and organizers.
Yes, sir. So let us conclude this session. Thank you, sir, for accepting our invitations. And as I told, it was really indeed interesting talk, and most of us, I think, are getting benefited from this. And thank you, sir, once again for your enlightening talk, sir.
See you, Dr. Satish. Thank you.
Yes, sir. Thank you, sir. We'll meet, sir.
Can I leave the
Thank you, sir.
meeting now? Okay.
Sorry,
Okay.
sir.
Yes.
Can I leave the meeting
Yes.
now? Okay.
Yes, yes, sir. Yes, sir. Thank you, sir.
Okay, bye. See you. Okay, bye.
Okay, sir.
Participants, there is going to be one more session at 3:30. So we'll take a short break and then we will rejoin at 3:30 p.m. Yeah. Thank you. Hello, Dr. Prasanna.
Hello.
Can you able to hear me? Yeah.
Yes.
Yes, yes. So, can you speak something so that we can check your voice is audible?
Yeah. So you can hear me or?
Yes, yes. It's perfect now. Yeah.
Okay.
Okay. So we will start the
Maybe I
session
can
at
just share
3:30.
my screen.
Yes,
you can see.
you can try now.
Mhm.
So there will be a green button to share screen.
Yeah.
Yeah.
So you can see like only a single screen now.
Yes,
I have like
we
two
can able to
monitors.
see your, we can able to see your screen. Can you just move the slides? Yes, we can able to see that. Okay. So,
Okay, but you can see only like one single screen now, not dual screen.
yes, yes, it's like a full screen now. Yeah.
Okay.
Okay. So we'll start the session in 5 minutes.
Yeah, sure.
Okay, so good evening, everyone. So I welcome everyone to this session. So this session, the topic of the title, the topic is optoacoustic signal and its applications. I am very happy to introduce the speaker, Dr. Prasanna Kumar Palaniyappan, to everyone. So Dr. Prasanna Kumar Palaniyappan is a senior researcher and principal investigator of German research-funded project in adaptive radiation therapy at Ludwig Maximilian University, Germany. He holds a PhD in biomedical engineering from Chunbuk National University, South Korea. He completed his master's in Sweden at Mid-Sweden University and bachelor's in India, specializing in electronics design and engineering. His doctoral dissertation involves development of real-time photoacoustic tomographic system and its target enhancement. His current project involves image registration framework using in-room proton radiographies for reduced imaging dose exposure to patients undergoing proton therapy. He has published numerous papers in the prestigious journals and conferences. Now I invite Dr. Prasanna to deliver his talk.
Thanks, Noel, for the introduction. I hope you can see my screen.
Yes.
Sunil? Yeah, okay.
Yeah.
So, so as Sunil said, so today's topic is optoacoustic signals and its applications. So right now I work in Ludwig Maximilian University in Germany, but this topic was based on my PhD dissertation from Chunbuk National University in Korea. So this is the outline of today's talk. So first I will start with some principles on what's photoacoustic tomography or the optoacoustic tomography, and the motivation behind the system, like why this is important in medical imaging system. And then I sort of explain the framework and how we built this system, the real-time system in Chunbuk University in Korea. And also we tested out some certain application, medical application, and also other applications. And then the challenges which we faced when we used the system, and then how we sort of improved the signals or the results from this real-time system using some signal enhancement technique. And then I will just talk about some related application relating to this optoacoustic signal, where they work in right now, in University of Munich. So, and then also explain a few slides about my current project, and if someone is interested, they can still apply for this. So going back to the history, in 1880, Alexander Graham Bell invented this technique. So he just used this technique not for medical imaging but for general purpose. He invented this photophone. So this is based on this optoacoustic signals. So what happens is you just need some medium or some surface where the light is absorbed, and then the temperature sort of increases in this local surface, and then thermoelastic expansion occurs in the surface. So what happens is you could get or acquire this incoming acoustic signals, the sound waves from this thermoelastic expansion, and then you could just measure this data. But this technique was initially used in some gas analysis in 1938. Only in 1960 the laser was developed. Until then, after this, in mid 1990s, it was very famous. Started pioneered in biomedical imaging. So in medical imaging, we sort of use this technique where you just use this acoustic pressure, and then to use this information to reconstruct some image, and then use this for some non-invasive treatment therapy. So you don't need really to do some excision or operation to the patient to just visualize some patient or visualize some tissues, or for example, some cancer cells. So you could use this technique just using a non-invasive manner. So this technique is right now, it's not not in the current market. Like you cannot find this in hospital yet, but say in another 5 to 10 years, you can easily find this in your local hospital or in some cancer treatment centers. So what the idea is, like as I said, like so here, like today I explained mostly about some animal or some biological mimicking phantom instead of humans. So for example, if you have some mice or mouse like in a stage, and then you shoot some laser in the particular location in the mouse. So what happens is like a local heating takes place in this position where the energy is absorbed and transferred to heat. So in the result, you sort of get this thermoelastic expansion, and then the ultrasound sort of emits in all directions. So the idea is to have some one single ultrasound transducer or many number of ultrasound transducer around this specimen, or you could just simply have like one single transducer and then use some motorized stage to acquire like a 360-degree of data. And what happens is like you could use this incoming signal like from the transducer and then collect this electrical signal and digitize and then use some image reconstruction algorithm where in the end, like you sort of get this 2D or 3D image to visualize some tissues inside. For example, if you have some hand and then if you have a human hand and then you just want to monitor some blood vessels or some movement in the blood vessels, you could just shoot a laser and then you could just visualize this in the photoacoustic image. So this is the general principle. On the right hand side, you could see some example or the prototype developed in Philips. So it's not like complicated setup like what you have for other medical imaging, but simply use this idea of the ultrasound imaging system and then combine this with the photoacoustic to get a photoacoustic system. So on the right hand side, you can see this monitor where it displays this photoacoustic image. And then you just have a small digital acquisition system for the photoacoustic system. For the acquisition, like we just use this commercial available ultrasound probe, so which comes with this ultrasound system nowadays in clinic. So we just want to integrate some laser to this ultrasound system. So you can see this fiber bundle where this laser light is like delivered to the patient in the same like handheld probe. So you don't need like a complex system. So the patient lies in and then comes for the treatment, and then you can just simply monitor where the tissue is or where the tumor is. In the left hand side, you could see this resolution versus the penetration in tissue. So if you want to see this organ or tissues, like initially we start with some linear array photoacoustic computer tomography, which is nothing but what I've shown here. So you just need some commercially available ultrasound probe to just reconstruct with a laser included in this. So you could really see some organs with this setup. And if you go further down, like if you want to see like cell or organelle or even sub-millimeter resolution, you just go for photoacoustic microscopy. So this is like really in development stage. I think it takes some time to really use this for a treatment center because of its complex hardware systems. And and in the Chambuk University, like we started not to go for the complex one. So when I was there, like we started to implement this linear array photoacoustic computer tomography, which I will be showing you today in further slides. So this is an example of this application. So in the middle, you see this photography taken from the camera. So here, like we don't really, they didn't really kill the mouse. So the mouse is a living specimen. So what they did was this, they shaved the head, and then they just acquired the photoacoustic image, like the previous setup I showed you. So this is like how you see this blood vessels, or you end up with after the reconstruction. And in the microscopy, you just have some micron range of 500 micron millimeter, for example, here, where you could see like in-depth neurons and other complex structures in the living mouse. So you don't really need to like cut open or kill the mouse. So this could be like a crucial imaging technique. In general, like this photoacoustic or optoacoustic tomography is mainly intended for brain lesion detection or the breast cancer diagnosis. But when we developed in Jambu University, like our intention was to use it for tumor treatment monitoring. Where you can we had like collaboration with some drug delivery team in the university, and they said they just want to inject some delivered drug on the mouse, and then if it's really like impacting the tumor or not. So this was our intention, and also like before testing this, we also need to see this movement across the blood vessels. So how this injected drug is delivering or transported in the blood vessels. So this too is like my application, or like I was like more concentrated during my PhD, and I will be talking about like the influence of this blood vessel monitoring today. Yeah, so this is the framework of the developed system in our university. So this was like mainly built in like by the laboratory called Advanced Biomedical Imaging Lab, and this is our team in university. So it's nothing but like what we did was like an sample stage. So it's you could bring in some mouse or another biological living animal, for example, and then or some phantom, and then keep in the stage. And initially, like PC like sends some instruction to the PXI. So PXI is the data acquisition system in our system. So you just send some instruction to the PXI, and then PXI just initiates the whole process. So it sends a signal to laser, and then laser immediately shoots and also sends a trigger signal to the PXI. And as a laser like moves on to the optical setup, and it's delivered to the in the sampling stage. And we just have this commercially available ultrasound system, and we just use some preamplifier to amplify the incoming signal with some passband filters to neglect some noises. And then what we do is like we sort of have this dual board, like where we could really take the transducers, the signal from the transducer, and then just feed it to the ultrasound system, so that you can have like two images side by side or on top of each other. So you know like where you're really tracking because of this information available in the ultrasound system. And this trigger signal coming out of the laser was really like used to synchronize the reconstruction of the image, and then the and then the incoming signal. Yeah, and then for the laser, we sort of use this pulse Nd:YAG laser. So it operates in near infrared wavelength. And then we could really have this control of this pulse power. So if you want more power for this to get more accurate results, or like more pulse duration or different wavelength. So, but all this was set up in the less than like ANSI limit, so which is the standard medical limits which you could use in hospitals. Yeah. And then for image reconstruction, we sort of adopted some image reconstruction algorithm called this universal back projection algorithm from Zhu from 2005. So the idea is to use this acoustic pressure and then thermoelastic expansion coefficient, and then use the speed of sound. So in different medium, so each tissue has like different speed of sound. So, and also like you have this coupling medium. So whenever you have this ultrasound transducer, if you go to an clinic or a hospital in everyday life, so they sort of apply this ultrasound gel to get rid of like the noise, or like enhance this the sound waves coming out of your body. So so you need to also account for the sound speed of sound for this medium, whatever you use. So either ultrasound gel or a different medium. And then you could see like how it reconstructs, or you have like number of spheres, like and then in the end, like you sort of get this in relative intensity of this based on this acoustic pressure on both lateral axis and axial directions. So you end up with some 2D images, something like this. So we applied this algorithm in our system, and then to initially test the system if it is working or not. So we needed to conduct some phantom test. So the phantom test was mainly to imitate some biological specimen. So you could see like the white layer here. So this was like a part of the stage, and then you could see some transparent material here, which was mimicking a tissue. For example, it is made up of gelatin and water in ratio with protein 80 to 90% and 10 to 12% of water, so that you sort of get some like some specimen of your flesh or like the biological tissue. And then inside here, like you see like a black line, or it's made about like a polymer tube. And what you do is like you sort of inject some contrast agent. So gold nanoparticles or silver nanoparticles or indocyanine green, methylene blue. These are like commonly used contrast agents during the cancer treatment. So what we did was like we injected this contrast agent inside the polymer tube, and then we just kept in between this gelatin layers. And then what we do is like we sort of set the laser wavelength. So each contrast agent has a different excitation wavelength. So you have to like set up this excitation wavelength and then just shoot the laser on this polymer tube. So this polymer tube is mainly mimicking the blood vessel inside the tissue. So in the end, like you sort of get some signal like where the laser is pointing, and then you could really get the signal or the structure of the blood vessels or the polymer tube, for example. So this is how the photoacoustic image after the reconstruction works in our system. So also to test the spatial resolution, which is like crucial for any system actually. To test this, what we did was like we did similar phantom, and we had like two polymer tubes, like making like two blood vessels with methylene blue, and then what we did, what you see in the right hand side is this ultrasound image. So you sort of see this distance between the 2 points, like outer edge, the inner edge of the polymer tube. And then what we did was like sort of minimize this distance in axial direction, so that in the left hand side you get this photoacoustic signal. You could really see this difference between this outer edge until like we sort of reduce this distance until where you don't see this signal like separated, or like if the signal overlaps. So and then we found out the axial resolution of our system was around 0.59 millimeter. And we did the similar experiment in the lateral direction. So you could see like two tubes here. And we reduced the distance, same as I showed you. And here, like in the ultrasound image, in the black image, you can see this overlay. Like, for example, if this is the photoacoustic signal, so it is overlaid on top of the ultrasound image, so that it's, you know really where you're looking at or where this signal is coming from. So it's a good idea to have always this ultrasound system in photoacoustic. You can also see this distance sort of minimized in the lateral direction, and once it reaches like 0.2 mm, so the signal, the system like could not really differentiate between the two signals. You could see the signal overlap. The lateral resolution was around 0.47 mm. So this was crucial, like when you do or perform like any sort of animal experiment. So today I'm going to show some results like which really it's not like a medical application or like used for the cancer treatment. So my colleagues there like had like collaboration with, as I said, like drug delivery team in Chembuk University, and then they sort of bring in or inject this drug inside a tumor infected mouse, and then they could really monitor this. But today I'm going to show you like a different application which I was working on. For this, like we had some collaboration in the same university, but with some environmental, social environmental group. So where they read this toxicology or how it's impacting the environment. For this experiment, we sort of like choose like a zebrafish. So this is like a quite interesting specimen because zebrafish has like a really like an optical clarity, so you could really see like what's happening inside the zebra fish. So here is like also like another important factor is like it takes only a few weeks to develop from embryo to adult stage, and it has like many number of breeding compared to a rat or other biological. So it was like quite a good choice. And then this study was like mainly intended for, as I said, like it was like environmental hazards. So in day-to-day life, we sort of use this cosmetics or other like beauty products. So what we do is like we sort of apply in face every day, and then we come home and then wash it in the later in the evening. So it sort of like dissolves in the water, but the antioxidants in the cosmetics, like for example, gold nanoparticles or other particles, doesn't really dissolve in the water. So what happens is like it sort of like goes to the ecological system, like goes to the river or your local local like environment, and then mix up with some marine animals. So it really like affects the marine inhabitants. Like so it depends on how much concentration or how much it is concentrated in single place, or how much this animal is really affected. So for this test, like what we did was we took gold chloride, which is really found in common cosmetics, and then made an extract or a synthesized with spinac leaves extract and then with water. So here in the left side image, you could see this the image from the transmission TEM, like the transmission electron microscopy. So you could see this different gold chloride particles inside the solution, ranging like from a size of like 5 to 40 nanometers. So which is like really like could go into the fish body and penetrate there or stay in the surface. And also on the right side, you could see this absorption wavelength or the excitation wavelength of this particles, which was around like 540 nanometer. So which was perfect for our system. So our system, photoacoustic system, which we developed, like had this settings, excitation settings. So what we did was like we set up this laser excitation at around 540. Like we set the laser to 540 nanometer, and then we just shoot the laser onto the mouse. The fish. And also like the fish is like this solution is like then mixed inside or poured inside the water tanker or the fish tanker, and then it treated for a few days. It just really requires like few days to accumulate in the fish organs, like our gills or something. And then we just kept the fish inside our system, like photoacoustic system. So for this like experiment, like fish needs to be like put in anesthetized state so that it doesn't move. So what we did was like we just put the fish in a cold bath, so in the freezing water, and then we just the fish goes to this hyper state where it doesn't really move, and then we just place this in for our system in our sampling stage. So here on the bottom image, you could see this fish signal coming from the ultrasound image, and also the photoacoustic signal on the top, which is overlaid, like to know which part of the body has like more the gold chloride particles. So it's mostly seen in the eye region or in gills where it could easily accumulate. But then like we could not really like since our resolution is like not too depth in depth, so we could not really identify which organs are how much like how much in ratio it's like saturated located in different organs. But the stuff is like we could really see this gold chloride particles or the toxic particles inside the fish. So we also made like some interesting publication. If someone is interested, you could just have a look at it. They also confirmed it different microscopic or in a cell level, like how much intensity or how much the particles is really found in each organs. So yeah, so the system works. So we could confirm with some phantom tests and then some animal specimens. As I said, like my colleagues were really working on this tumor tracking in the mouse, for the mouse treatment. So where they inject the drug and then they could monitor this in the blood vessels, how it moves. So on the right-hand side, like some images which comes out of the photoacoustic tomography. So you could see this noise coming out of this the image reconstruction or the complex hardware structures. So you could see like certain ring sort of shapes comes out of this acoustic signals. So here, like our object of interest is only the blood vessels, but we also end up with noise. Also, like here, like you could see multiple lines, which is actually like the layer or the edges of the polymer tube. So you could get the inner wall and outer wall of the polymer tube. So this was also like affecting our signal. And another case is like when you have like multiple blood vessels or multiple polymer tube, you sort of miss this signal at certain points. So it's not like continuous, which was really crucial, like, because we always need to monitor the flow of the drug. So so the challenge was like to, how to get this the nice blood vessels information and then exclude all the other background. So for this, like I was working on improving actually the photoacoustic signal coming out of the system by just playing with the coupling medium. As I said, the coupling medium can be either the ultrasound gel or some water. So you just need to, so I was just working on this for the first topic. And then the next one was this, the image processing algorithm to segment this blood vessels. So this was like not the real-time system, but it was just a post-processing. Yeah, so first I'll talk about this signal enhancement based on the coupling medium. So, so as I said, like normally, like they use this ultrasound gel or water to optimize the transmission of the sound waves from the scanned object to the ultrasound transducers. So what happens is like, the speed of sound travels like faster in different temperatures. For example, lower temperature, like it takes time for the speed of sound, but when you have like higher temperature, the speed of sound travels faster. So that this was the idea to increase the to play with this and get the more signal enhanced in the photoacoustic system. For this, like we conducted like two studies, like using a one-dimensional system and then also like the two-dimensional imaging system. For the one-dimensional system, what we did was like we had like unfocused like a single element ultrasound transducer. So what happens is like it has like only single element of the transistor, so that it gets only like one signal at each time. So it's not like you could really reconstruct an image, but it's a good starting point. And then we have this for the laser delivery side, we need the laser to be delivered inside the water. So we had like fiber optic line lights. And then we just take this ultrasound signal with the pre-amplifier circuit and then just use some oscilloscope to read the signal and then just synchronize with the trigger signal to get the data in the PC. And also like we need the water in the water tank. So it needs to be like, hot water coming in one direction and then the cold water in other direction. So the water needs to be circulated. And then you need a thermistor or like some temperature reader. So we use like some in NTC thermistor to read the temperature current value of the water so that we could calculate the speed of sound. So this was like in the 1D system. So for the calculating the speed of sound, you just really need the salinity of the coupling medium. So either the salinity of the ultrasound gel or in our case, like salinity of the water. So in the end, like you could really get the speed of sound based on the current temperature values. So yeah, so you could really see like how much it changes between 20 degrees Celsius. For the 2D imaging, we also need this tissue dependent constant. So during this attenuation coefficient constant, we use this attenuation coefficient constant in the reconstruction algorithm. So you also need this speed of sound coming from the thermistor, and then it just calculates the speed of sound every frame and then use this while reconstructing the 2D imaging. So in general, like our system had like I think around 12 frames per second. So when we don't use this any sort of signal enhancement technique or this optimized algorithm using the new speed of sound, but when we use this speed of sound algorithm inside the real-time system, so the acquisition was like very slow. So it was like 2 to 3 frames per second. So, but still it was, we could end up with higher intensity in the PA signal. So what we did was like we took some baseline photoacoustic frame where we don't at the room temperature, for example, and then we just compared how much the intensity is increasing as the temperature is moving. Yeah, like for the phantom test, like like we had this indocyanine green, so we just inject this in the polymer tube, and then we just seal both the ends so that water doesn't dissolve in this contrast agent. And also, like after I left the group and then I moved here, like so they also did this experiment using some animal models. So what they did was like they had like the tumor in the end of the mouse in the lower part of the body, and then they injected and inserted only this lower part of the body inside the water tank, and so that like the mouse doesn't drown, so that you could still acquire some signal enhanced image. So these are some results from the 1D study and 2D study. So you could really see how much the photoacoustic signal improves over like 5 degrees or 6 degrees of temperature. And also like if you consider like in 2D, like after this 2D image reconstruction using this updated speed of sound, you could see like in the figure A, like you could see in for 27 degrees Celsius and B around 35, you could really see how much the signal actually improved. In general, like it was increasing the signal for every 1 degrees of Celsius, it was increasing about 12% of signal, which was really like promising. And then we also stayed like below 40 degrees, so it might not be like a favorable like when you use this sort of technique in a hospital. So you just need to be stay in a certain limits where the patient doesn't feel uncomfortable. So now the signal is enhanced. So the next one was like to play with some image processing techniques. So for this, like we sort of like used image segmentation techniques, which is nothing but like you sort of select a region of interest. For example, in our case, like the blood vessel, and then we just want to get rid of all the background noises. For this, you could just simply give a threshold value, like based on the intensity. For example, you could get rid of this gray image and then just have with a higher intensity image. But this doesn't work for all the applications. So we need some unique algorithm to work on all the cases. For this, like we sort of used a model called the active contour model based on H method and region-based method. First starting with the H method. So in the H method, what happens is like, for example, if you have an image with an like the green color here inside the image is like the local representation of the image. What the H direction does is like it processes it's the process of labeling the locations in the image where the rate is high. So it just calculates the rate of change between the object and then the background. And then you end up with a term called the edges, which has this location, direction, and the strength of each object. So and then what you do is like sort of integrate all this edges information to get some continuous boundary around the object. So the blue color line sort of just connect all this edges information to get this blue color line to form some object. So in the left-hand side, like you sort of have this ultrasound image, which was similar to what we had the ultrasound image in our case. And you could see some fetus structure inside the ultrasound image. So the idea is to segment this, the fetus apart from this, the background noises. So for this, like what we do is like we sort of have this initial mask or initial region. So you need to give some initial region around this object, and then you could see this the green line here, which usually represents this initial or the original curve, which they mention, and then it sort of moves towards this, it calculates this edges, as I told you, and then it sort of moves towards this local minima inside this object. So if the red line is like, it has this minimum value, then the green, and it's the local minima of this, the defined boundary. So also this technique, the active contour model, is like, it's not like a single step. So it's like an iterative processor. So every iteration, you need to define some iteration, and every iteration, the function or the optimization function, like it calculates the local minima and then calculates the error, so that it moves towards the local minima after like many number of iterations. So it just stops after finding this local minima. So here the red line. So this was the edge method. But for the region-based method, it's more like simplistic, but also like less time consuming. So what you do is like you sort of divide this image or your image into several regions, like subregions, and then you sort of define this initial boundary or the initial curve, and then it sort of evolves in this iterative process. But for this, like you just need two coefficient, which is based on the inside of the curve and then the outside of the curve, inside of the contour and the outside of the contour. So for example, if the black objects here is like your object of interest, and if the curve is, or if the initial curve is like outside of this region, so it's sort of like it doesn't satisfy the condition, but it sort of like shrinks to a point like where it reaches like for example here, like if it reaches like a point inside the object, it needs to expand, so it doesn't satisfy like one of the conditions. So but when there is a case like where the initial curve is like inside and outside, what happens is like during this iterative process, it sort of like shrinks and expands at the same time. So in the end, like we sort of get this fitting to the local minima based on to the object of interest after like many number of iterations. So this was like the region-based model. So yeah, so in our case, like we sort of implemented this two technique to see how this we could how well we could segment this blood vessels. So this is like initial boundary region which we define. So the every iteration, like this sort of the initial curve sort of moves towards the local minima in our case here. So here you will see this magnified results. So the edge method is like it sort of identifies this object, but it has this subpixel error. So you could see this error in the subpixel range. So it's not really like 100% accurate. It's not like accurate as like the region-based model, but the region-based model is like, it's well defined, and then it sort of identifies this very well. So these are some of the accuracy measurement which we did. So for this test, like we took like the blood vessels or the phantom test using two set of data. One is using the indocyanine green and then the methylene blue contrast agents at two different excitation wavelength. And we also played with the initial region, like the mask region or the mask size. And then, we could plug in this to this active contour model, this iterative functions. And after many number of iterations, you sort of end up with the accurate results of the segmentation of the blood vessels. Comparing both the method, so you could see like the RB, like here, like you have this accuracy scale. You sort of get this higher number. So the higher the number is better. So how we calculate this accuracy is, we just compare this with the ground truth image. So the ground truth is nothing but like a manual segmentation on the blood vessels. So we did a manual segmentation to get a nice subpixel accuracy, and then we just compare some the two images coming out of the one coming out of the active contour model and then the ground truth, and then we just compare this dice similarity coefficient. So usually if it is 1, it's highly accurate, and if it is 0, it's not accurate. Yeah, so as I said, like we got like better results using the region-based model, but there was like our application had like few number of vessels, blood vessels, but in the end, in theory, like or in practical, you could also have like something like a many number of vessels, like here It's not actually the photoacoustic image, but an image of an retina from the eye, and you could see like you know how well is the vessels are connected here. And when we applied like you know the H model and the region-based model, you could already see this you know like the error coming out of the H model. It's not like highly accurate as this region model. And another thing is like you know when you have this sort of closed structure, so you know like the H model doesn't know this is like an you also have some vessels inside, so it sort of stops here in the local edge of this region. So it doesn't really move inside this object where it's like you know fully connected. For this, like you know, region-based model is better because we could apply like you know many number of multiple masks initially, like in many regions, so that you know the curve sort of evolves in different spaces, so that you could really get all the information, edge information from the from this sort of blood vessels type. Yeah, and also like the signal to noise ratio is like you know better for the region-based model compared to the edge-based model. Yeah. Yeah, to summarize this optoacoustic signal, like you know the work I did on the Chembuk University, like you know the system was like a real-time system. It has like 12 to 15 frames per second before applying this signal enhancement model. But yeah, we could really see all the contrast agents are traveling through the blood vessels, also in the mouse, which I did really like show to you today. But it also worked in the toxicology study where you could see this, you know, the nanoparticles coming accumulated in the zebrafish. So the system was working really, but we also needed some sort of like accurate like image processing technique or other techniques to make it like you know more clinically feasible. Yeah, and also like you need to find some trade-off between the real-time system, the acquisition time, and then the processing time for this sort of enhancement techniques. Yeah, and also another thing was like when I was working 4 years before here in Korea, so we had this linear acoustic computer tomography, but we never really moved to the photoacoustic microscopy. There is this the group from the environmental studies, like you know where they confirmed this zebrafish toxicology using some other microscopy, like where they could see this toxicology in the cell. They also identified like you know if the zebrafish mother is infected with this sort of toxicology, like the nanoparticles, it also passes through this embryo. So the baby is born already with this sort of nanoparticles, and it could really die in few days. But we couldn't really like confirm this with our system because our spatial resolution doesn't really support the embryo detection. For this, like they were working on developing the photoacoustic microscopy, but not sure in which step they are right now. But it's like a positive hope to work in this direction because we already confirmed this in the photoacoustic computer tomography. Another related application is like the one topic where they work in my university right now in our chair. They sort of use the same principle of the thermal expansion and then detecting this acoustic waves and then use the signal in other applications. It's called like the Iron Acoustics. I think you are all familiar with this treatment, cancer treatment. For example, the Cancer Institute area, which usually operates in the photon range, so they use only the photons. And also there is a cancer treatment center in the Apollo Hospital in Chennai, where they have this protons. So you could see this photons now. So this is the tumor range, and you could see this photons. You know, like when you shoot the photons on the cancer cell, like it sort of like also destroys this nearby, like you know, normal cells. It also destroys the tumors, but you know, it also like destroys this normal cells. So this was like side effects of the photon treatment. So if you have like cancer in like a non-risk region, for example, in some lung or so other organs, which is not like so crucial, you could really go into this cancer institute in area, so it's not really going to make so much difference. But if you have like cancer in head and neck or some brain tumor, so you could really opt to this protons in Apollo, but it's quite expensive compared to the photons. But you could see like, how it penetrates into the body and then how the dose are delivered in certain range. So here the black region is like your black line is this main the main range which you intended, but also this has some range uncertainties. So it also has like few depth millimeter, so it could also like destroy certain normal cells. But this was the main topic which people nowadays working on this field to minimize this sort of range uncertainties. So here like in our team, like we sort of use this try to like find this acoustic or the optoacoustic signal, not optoacoustic, like the ion acoustic signals for calculating this range verification techniques. So they sort of like calculate this localized energy deposition on your body. So yeah, as I said, like this photoacoustic, optoacoustic or photoacoustic tomography, it's not like only for the non-invasive imaging, but also like it's expanded in different fields. Yeah. And also like one slide about like my current topic. So right now I'm not really still working on the optoacoustic signals, but I also support this this team here in university with our colleagues. So I support some students and stuff, but I'm not really like 100% working on the same field. But I sort of moved to a topic called radiography-driven deformable image registrations and adaptive proton therapy, which is funded by German Research Foundation. So here, like the goal is to, like every time if you go to an radiation center or the proton center, in, for example, in Apollo, what they do is like you have to visit like multiple times. So every time they have to like align the patient couch or track the tumor like based on the your first time visit. So for this, like what they do is like they sort of get more X-ray CTs or the cone beam CTs to track back like how much you have changed, the tumor location has changed, or the location of the patient couch is changed. For this, they use this typical like X-ray CTs, but this really has like a disadvantage, like higher dose exposure, imaging dose exposure for the patient, and although the imaging quality is not good. The idea is to use like some certain detectors in the proton centers and use this information like which passes through the patient, the protons, and then use this information to reconstruct some 2D ion radiographies. So we just need like 2 or 3 ion radiographies, like limited number of radiographies to track the tumor location or the patient locations, and then we could just use this information to move the patient couches, for example. So this technique we call this 2D, 3D image registration. There are several publications in this topic. If you are interested, you could just look into it. And also like this is our website for our chair here in LMU. Yeah, we usually have like a master thesis or a PhD or postdoc every now and then. So you could really look into this if you're interested in this topic. And also like for the master students, you don't really get stipend for master thesis, not really like so much. You could really support here. So you could use this DAAD to support yourself during the masters. So this is like some scholarship for the students. And the bottom one is the Humboldt is for the postdoc position. Usually the acceptance ratio here is good, very good. So you just need to write a proposal for 3 or 4 pages, and then like every one person in 3 application gets accepted. So it's really good. And also, like I like to thank my whole team in the Advanced Biomedical Imaging Lab in Chembuk University for 4 years of working in this photoacoustic topic, which is quite interesting. And also, I like to thank my current team in my LMU and also all the audience. Thank you for your attention.
And thank you, Dr. Palaniappan, for the insightful talk. It was really interesting to see that you're working on some of the advanced topics that yet to be in commercial markets. I have few questions. Would you be would you be interested in? Yeah, please. Yeah. So I've looked into your the built-in system that you have developed in South Korea. I wanted to know whether the handheld the sensors can be used to capture the images, like the transducer that you used. Okay, is that the general way, or do you?
Yes. Here, like in the right side, you sort of have this image now, like photoacoustic image reconstructed just from the single transducer. You don't really need like multiple transducer or a rotating stage to get a 360 volume or a 3D volume. So the image which I showed you, like, for example, here, it's just like, using this linear array. So transducers, like for what you see here, we call this a linear array transducer. You could just reconstruct a 2D image from this information.
Okay. Yeah. So I also have seen. So this one is a linear one, and there was some kind of a rectangular array, like just like some CMOS sensors. Can also be used, is it?
Yeah. So the idea is like not to use a complex transducer or to make the system complicated, just to have this in already existing ultrasound imaging model. So this ultrasound system which you see is like from the Philips. So you could see hospital or somewhere, and then you could always use like whatever sort of transducer they use. I think this image was like from 2011, so it was a prototype, but right now this might be like evolved more. So the transducer might be like even more advanced. When I was working, like they also had like this sort of transducer. It's not really connected to the system, like using some cables. So they had like a mobile phone where you could see this ultrasound image, and then the wireless Bluetooth transducer. So you could just move it wherever you want and take wherever you want.
Okay. So what is an ideal penetration depth for a better penetration depth? What is an ideal wavelength we can use? Suppose if you wanted to image a tumor inside a living organism, let's say mice or any living organism, what is ideal penetration? Yeah, what's an ideal wavelength can be used?
So it depends on what sort of system you use. For example, here in this image, the left side, we have this chart now. So the linear array photoacoustic tomography, which our system, like when we built, was like in this sort of range where you could see the organs. But also like in this image, like what I've shown you is like based on the photoacoustic microscopy. So this is a complex system. So it was developed by Li Hong Wang from US. So he's like really a pioneer in this field. So, but if you, I think I also have this image. So here is like in this book, like, you sort of have this photoacoustic microscopy system. So it's kind of complex. You cannot really bring this system to a clinical field. It was like how it was developed before, but I'm sure like it might have improved a lot right now. But if you want to really see the organs or the organelles or the cell, it depends on it's usually good to have this microscopic level, photoacoustic microscopic level.
Thank you. And recently I've seen that there's a commercial system called the Vivo Laser, which does the photoacoustic imaging. I think we can buy it from suppliers. Like they have where we can go ahead and buy it, just like the ultrasound imaging system, where we can buy it and we can take an images of photoacoustic, the photoacoustic imaging. I hope you might have seen that in the internet. It's called VEV.
Yeah, I think like when I was like I worked on this topic like 4 years before. So when I like really left this group, so they had a collaboration with Samsung Medicine. So in Korea, like they conducted this not with our system, but Samsung Medicine also like had some principles or the code or the framework which we developed, and then they used it in their own sophisticated system. So it was expensive more, and it's more like their aim was to develop this for a commercial product. So when I was there, like actually in 2018, they sort of did this experiment in the pig. you sort of move from your mouse or other sort of small animal to like a big animal. So pig is like, one step before the human trial. So, but I'm sure like they also tested in the humans. But I'm not sure like, the timeline for, when you can get this in hospitals or in the clinic. So it might take another 5 years. So it's not very far, but it's really like a non-invasive. So you don't need to cut down, the tissue or to see this tumor during the treatment.
Yeah. So thank you. So there is another question from Mr. Shamakumar. He says that what are the other factors except water and oxygen, fat from the human tissues? Are there any other factors that affects the imaging quality? Imaging quality whenever you take in vivo imaging.
So when we reconstruct this image, like we always consider this tissue dependent constant. So each tissue has like different speed of sound. So you need to account for this tissue dependent. They call this as a brunation parameter during this reconstruction. So other than this, like when you use ultrasound gel, for example, as a coupling medium, so this is very common. You sort of end up with air bubbles. So when you have like a few centimeter of this ultrasound gel, you could, if you are not so good at this, operating this, you could end up with air bubbles in between. So this sort of like introduced like different medium. So when you set up whole system and then you have this sort of noises, artificially introduced by the humans or the clinicians, it changes like the accuracy of the image. So yeah, you need some expertise like handling this ultrasound gel. I think if you go for an ultrasound treatment or imaging like in a hospital, like usually the people who do this like take care to avoid the air bubbles. But in ultrasound, I think it's not impacting so much, but the air bubbles really impacts. I think I explained this like when we had this water tank set up for a temperature controlled system. We need this. We cannot really pour hot water inside the water tank. We need this circulation going on, so from one end to another end. So otherwise, like you sort of like air bubbles forms in this layer of the sample. So it really affects the output quality of the image.
And just out of curious, so the ultrasound signals that's coming out from the or the signal that is coming out from the tissues, is it scattered one or it's a scrambled? Like how does it look like? Is it a straight imaging thing, or do you have to go for some face retrieval thing or something? Like how do you reconstruct the image there?
So the thing which we use for photoacoustic was like the back projection algorithm, but the ultrasound is like which we use, which I showed you in the overlay images, was like the commercial ultrasound system. So it just uses like normal ultrasound image reconstruction. So
okay, thank you.
Yeah.
Are there any questions?
There is one more question from Bhuja.
So have you ever heard about these drug response systems? Like I have seen a couple of papers where people working on photoacoustic technology for identifying what type of effect does the drug has whenever a patient consumes a drug. Have you explored in that sort of research?
Yeah, I think I told this point, like, I didn't add this result today because it was not like my part of my thesis during the 4 years, but my colleagues and the team, which I showed you, they were working, they had a collaboration with some drug delivery team in the university. And, like they sort of like artificially induce like cancer cells in the rat, in the mouse. And then they treat this mouse using some of their own developed drugs. So, yeah, so before this, like, every time they use this drug on an animal model, they have to test this on a phantom to check how it works. So they use this on the phantom which I showed you. So this was the main aim using this segmentation algorithm or the enhancement technique to identify this blood vessels. So the main goal was to support this work or support this, use this idea in the drug delivery team. But they also published in our team like using tracking this drug delivery in the mouse. Yeah, I think I also said about the mouse, like where they injected the drug and then they monitored like the flow in the the temperature control system. So they had this mouse in the lower part of the body, and then they could really not drown the mouse. So the mouse was like only halfway in the water, and then they could get the enhanced signal. So yeah, the system really works in tracking this sort of contrast agents, because the contrast agents, like in all the drugs, like what they do is like they sort of do binding with some contrast agent, so that you can have the bioluminescence properties now. So it sort of always emits when the laser is exposed, when you expose this in the laser, so it excites, and then you could really track this drug during the treatment.
Thank you. So was it pad system, or what was the?
It was like pad system. So it was a photo, like the linear array. So we could really see in this linear array transmit setup.
All right. Okay. Thank you. So one of my colleagues, Dr. Sadish, would like to ask a few questions.
Okay. Thank you, Dr. Prasanna, for your interesting talk. I will ask my question, but before that, I can see one more question from the participants. How to link this with IoT for better healthcare system?
It's kind of a tricky question for me, because it's not like the one field which I was working on, the IoT things. I think you guys have more expertise in this. But yeah, I think as I told, like nowadays you have this ultrasound system where it's like you don't really need a huge complex system and then you connect it with a bunch of cables. But yeah, there are like handheld probes, so it sort of transmits this ultrasound signal Bluetooth in a mobile device. So you don't need really the system which I showed you here. You could see all the images in the mobile. So there is already information transmitted using the Bluetooth now. So you could use this technique or transfer these techniques to any sort of smart. Yeah, but I think like it takes some time, because for the ultrasound, for the photoacoustics, because you need this laser coming in with this transducer. But I think you just need this sort of like information coming out of the transducer with just electrical signals coming from here, and then reconstruct for the photoacoustic tomography. Maybe not sure if I replied to this question, but.
Okay. So, Dr. Prasanna, it's really interesting talk to me, especially because I'm working in this model communication, and with that context, and also the context of a speaker in a studies talk, she was delivering a talk on terahertz communication. She was telling that we can use terahertz communication for in vivo detection, and the research area which I'm doing, this small communication. The biggest motivation is that other signals may damage the tissues or cell of the human body if you are going to exploit them for in vivo detection, especially for the case of cancer. And today's talk, I can see you're also working on this in vivo photoacoustic tomography. So I have a curiosity that I want to know, really, do you have just, if you can enlighten us, that which signal is the best in terms of harming less to the living body? They can be good at their end in terms of giving high accuracy for the disease which we are looking for. But I am curious to know which signal is actually good in terms of giving the best performance, but that to the damaging very less the tissues or the living cells.
Yeah, it's quite an interesting question, sir. I think it really depends on.
Yeah, sorry to interrupt you. The thing is that the small communication uses chemicals to diagnose the disease. You have sensors, and say if some tumor is releasing proteins, we can use it as a biomarker, and the nanosensors can sense those proteins. And this way, the small communication works. So they claim that this is the most friendly type of communication, the promising one, because you are basically using the chemicals which is already released inside the body. It's biocompatible. You're not going to basically disrupt the environment. Now, in that context, basically, I want to know which is the best mode of communication for this type of disease diagnosis.
Yeah. It's two things actually. Like, it depends on how in depth you want to see the tumor, for example, inside the human body. So if you take this photoacoustic linear array tomography, so you could really visualize only the organs now. So, but I think, like, in general, like the ultrasound system is very effective, and then it doesn't really harm, because it's like, only you're making this sound waves and then just making this as an image. So also, like, when it comes to the optoacoustics or the photoacoustic combined with this ultrasound system, you just need this laser excitation now. So also, like this, I think I explained this, but we always stay in the ANSI limit. So this is like standard limit for the commercial or the usage in the hospital or something. So we never really exceed this limitation in the laser power or the laser strength. So we always stay below this range. So it's not like harmful for tumor tracking, for example. But in certain cases, like, in the application in toxicology study or in the biomarkers, like where you explained. So it's kind of crucial to have a certain type of like this contrast agent or the biomarkers. So if you have like gold nanoparticles or silver nanoparticles, it doesn't really dissolve in your human body. So you could use this for a contrast agent or during the treatment. But this is really harmful in the end if you take as a treatment. But right now in the treatment of this ultrasound or in the tumor tracking, they were using this indokinin green or the methylene blue. So it's just the dye. So it's not like it dissolves in your body after a few days. It doesn't stay long. So yeah, if you use like this kind of contrast agents or the biomarkers, I think the photoacoustic combined with this ultrasound systems is like really effective. Does
Okay,
that
thank you.
answer it? Yeah.
What do you say?
So if there are no questions, probably we can end the session. Thank you again, Dr. Prasanna. Thanks for a nice talk, and thanks for time for accepting this invitation and delivering the talk here. Thank you. Have a great evening.
Thanks. Yeah. Thank you very much.
Thank you. So the participants, we have 2 more days for the FDP. We will start tomorrow at 2 p.m. Thank you, and I'll see you all tomorrow. Thank you.